So in this last lesson, speaking about fuel cell, we need to focus our attention on the different types of membrane that we can use, so the chemical nature and the main important aspect and characteristics. So basically we have defined how proton exchange membrane and even anion exchange membrane represent the best types of solution in order to ensure the passage of cations in different types of cells. So for instance, maybe the fuel cell, the proton exchange fuel cell, also the direct methanol fuel cell, and so on. Sometimes this passage of cations could be even ensured with the use of natural substances, as for instance beta aluminum or other. But obviously most of the time the capability to understand the chemistry behind a synthetic ion exchange membrane is fundamental, it's crucial. And so now this is the reason for which I want to make this lesson about the different types of membranes that we can appreciate mostly in the fuel cell. So in general there are two main types of proton exchange membrane, or in general ion exchange membrane used in the fuel cell, and these membranes are respectively Nafion, that is a fluorinated polymer, and polystyrene. Polystyrene, known as PS. Cross-linked polystyrene, to be more precise. So, for what concerns the Nafion, we can say that this is used mostly for the vehiculations of cations, even if it could be modified in order to create an ion exchange membrane. Whereas the cross-linked polystyrene exists as a mature technology already also as cationics exchange membrane and anionics. The Nafion is mostly nowadays used for protonic exchange membrane, even if more studies are proceeding in the generations of the best types of anionic exchange membrane due to a Nafion modification. So we will see also this aspect. So at the very beginnings, I want to describe what is the structure of the Nafion, this fluorinated polymer. And this structure is basically this one. So we have a quite huge amount of different repeating units that can be repeated in different times within the main structure. Is a fluorinated polymer having these characteristics. So M, N, X, and a generic final group. And this generic final group, it could be, for instance, a weak acidic function or a strong one. And basically this means that in according with the value of pH we can select what it could be the dissociations of this group, and so the anionics character of this polymer, and so the capability to derive protons. So this is for what concerns the Nafion. But then we have even cross-linked polystyrene. So cross-linked polystyrene is another type of very quite useful polymer for the membrane in fuel cell. And in general, the structure is something like this. So we are using, with these radical polymerizations, a bifunctional polystyrene as a monomer for this polymerization with different types of initiation techniques. Because in this way we are able to create a bridge between different macromolecules and proceed with the generations of our cross-linked polymer. Also, in this case, we are able to tune different groups present on the aromatic ring, conferring a weight character or a strong one in this case. So now it's important to say that regardless the types of the chemicals used in order to create our membrane should be characterized with very specific characteristics. Not only the capability to vehiculate the wanted cations, and so maybe a certain permeoselectivity that is really pronunciated. The permeoselectivity could be defined as the capability to vehiculate one specific ions with respect to counter ions. And so we want to describe these in terms of transference number. We can say that the transference numbers of the cationic species, for instance, associated with the vehiculations of cation, should be equal to 1. So the total conductivity should be associated with the movement of the cation. So the permeoselectivity is obviously the crucial key aspect of our membranes. Together with the permeoselectivity, we need to have other characteristics. A quite high ion exchange capacity. An ion exchange capacity is defined as the amount of mole of cations that could be absorbed per unit of weight. And obviously also the equivalent weight is literally 1 over the ion exchange capacity is another crucial parameter. So the permeoselectivity, the ion exchange capacity, and so the equivalent weight are basically the three most interesting characteristics and parameters that can define if something could be used as an ionic exchange membrane. But together with these characteristics, it's crucial also to have a good chemical resistance versus alkaline and acid environment situation. It's important also to remember that we need to have a good high thermal resistance, expressed in maximum of high temperature we can use, the maximum working temperature, and high mechanical resistance, the capability to support and resist versus different changing in the pressure between the compartment of the cell, and also a capability to have a huge electrolyte uptake, to be swelled with specific solvent, for instance water if you want to obtain it in a wet state, and also the gas permeability and the electrical resistance are crucial, because we want to avoid passage of electron, at the same time we want to avoid the gas crossover. So basically we have a lot of different types of characteristics, and select the right types of membrane for a well-precise application is a quite complex science. So now, after I've defined basically different types of cross-linked polystyrene and the Nafion, different types of proton exchange membrane, is important to understand which types of anionic exchange membrane we know. So we know that in, for instance, some application, we can even use an anionic exchange membrane. So for instance, in alkaline cell, in which basically we can use as a fuel both hydrogens or methanol, and the vehiculation of OH- is responsible for closed circuit, fighting also the possible methanol crossover due to the opposite movement of these anions inside the membrane versus the possible movement of methanol during the crossover. So basically, it's important also to remember the possibility to create an ionic exchange membrane. And nowadays we have two main types of ion exchange membrane. The first one is radiation craft membrane. That in general is composed in ethylene tetrafluoroethylene, that is a copolymer having this structure. so a unit of ethylene and a unit of tetrafluoroethylene. And when this polymer is irradiated with a specific electron beam, what we can see is activated in an excited state, and it can react with specific molecules, and we are able to introduce these molecules inside this polymeric structure. And then, after I've introduced these molecules, for instance also something like this, in this polymeric structure, we can maybe modify it, for instance, with a conventional nucleophilic substitution, and we can obtain the final structure of an anionic exchange membrane, for instance. Ethyl, methyl plus an interaction with OH minus. So this is the first type of anionic exchange membrane that we have described, but we've also the possibility to exploit Nafion. But Nafion, we know, is a quite interesting membrane for what concerns the vehiculations of H+, a proton exchange membrane, but could even be modified with a specific treatment in order to allow the movement of these anions with respect to protons. So, for instance, the well-known structure of Nafion should be rewritten here again. For instance, it could be an example. And when these molecules can react, for instance, with this species, having a tertiary amine function here and a secondary here, what is happened is that we can appreciate these types of reaction. So what's happened is that here we can have the interaction between this group and this nitrogen group, and we can obtain these types of species. And with a further reaction with this reagent, we can finally obtain our cationic character, fundamentals and crucial for the calculations of an ion. So even we can exploit modification in the structure of the Nafion with this specific reaction. So the first step is this one, and the second step is this one, in order to obtain this final product. So basically now we have defined the main types of proton exchange membrane, and the same also for what's concerned the anionic exchange membrane. But it's crucial to describe that the anionic exchange membrane are often affected with different types of problem. First, we can have a pure diffusion coefficient of OH minus with respect to H plus, and this is quite important problem. And a really important problem is also that this anion is quite more reactive with respect to H plus. And since it's more reactive, it can react with this structure, for instance, in order to change the composition and degrade the membrane. Because this OH minus can react with this function, with different types of degradation mechanisms. We will see in a moment with these three or four main types of degradation mechanisms, and time after time we can appreciate the degradation of this compound and the loss in the character and in the capability to veiculate OH minus. So now let's focus our attention on the degradation mechanisms of these types of membrane. Anaionic exchange membrane degradation mechanisms. The first one is it's basically the Stevens rearrangement. So the Stevens rearrangement involves basically the terminal group of our Nafion membrane, for instance. So this is our final function R1, R2, and R3. Here we have this, and here we have the positive character and the corresponding anion. What is happening is that we can have that this species act as a base and can collect, extracting these protons from this side. If this happens, we can have the eliminations of water, since this hydrogen is collected here. And at the same time, we can have that this species is associated with now a negative charge here, and the positive charge that obviously is again present on nitrogen. So what happens is that we are filling this deuterionic character, and we can have a 1,4 shift, a specific rearrangement known as Stevens rearrangement, leading to the changing of one of these alkyl function here. And maybe we can have something like this, and we are losing the cationic character of our species that are crucial in order to evacuate our H-, since we need to have this physical interaction. So we have a 1 shift rearrangement as a result of this interaction between OH- acting as base toward this proton that is extracted from the structure. A quite similar types of degradation process is the Hhauser rearrangement. So Hhauser rearrangement. This type of rearrangement is a true free shift rearrangement, in which basically we are involving different types of membrane in which an aromatic ring is present. So we have, for instance, our function, cationic function here, with the corresponding methylene group. And what's happening is that, again, here we have OH-, and in this case it can extract one of these protons present on the methylene function here. And this leads to the fact that a negative charge is created here, and we can have, so with the eliminations of water obvious, we can have here that a 2-3 shift Hhauser rearrangement occur. So this function is collected here, and this remain in this state with a nitrogen here, and then this proton is collected again here, and so this unsaturated function became a saturated function's methyl group, and the final result is basically this, with again losing of each single cationic character, and so the capability to interact with the OH-. But basically again, in this state, the degradation is due to the reactive behavior of H-, as in the case of the Stevens rearrangement. So we have from one side a Stevens rearrangement, and from the other side the Hhauser rearrangement. But basically, the types of behavior, it's quite similar. We have the quite reactive OH-, And these anions is responsible for extract the proton that is start to promote the formations of this rearrangement, and this rearrangement produce the losing of the proton, the cationic character of our membrane, and so the capability of the membrane to veiculate further anions. So the last type of, was the second one, but the last types of degradation mechanisms, it is also the more important, if the Hofmann degradation. So that is basically a beta elimination mechanism. So a beta elimination. What is a beta elimination mechanism? Basically, if we have a saturated structure, something like this, R1, R2, R3, R4 for instance, and a possible X-kin group. So if we have here some nucleophilic species, maybe in this case or H-, this can extract one proton as always, creating a negative charge here. When this negative charge is created here, can be taken in order to create a double bond, and here we can have the eliminations of the S-kin group, and so we can have the creation of this species plus L minus plus nucleophilic with this, for instance, water. And so basically we are also in this case eliminating our cationic character due to the use of the presence of these quite reactive anions. If you want to describe this, for instance, more precising in the function that we well know in Nafion modified membrane, for instance, in this case, the hydrogen interested is this one. So this we have plus, minus, or H minus. We have the interactions here, we have this Hofmann degradation, this beta elimination, we have the formations of a negative ion here and the generations of water as a product, and here we have this and the eliminations of this group. And so what is to remain here is this and this species. So we have eliminated, basically, obviously this is not present anymore, we have eliminated again our cationic character, in this case with the Hofmann degradation and beta elimination. These represent probably the most important types of degradation mechanisms that we can appreciate in the degradations of anionic membrane.